Let's welcome Evan Yang to CAMLIS for speaking.
Thank you for the introduction. So today I'm going to talk about towards a trustworthy and resilient machine learning classifier. So this is a case study of the ransomware detector creation. We know the trustworthy and resilient is most two key points for our classifier. And hopefully, I believe this is a 101 talk for security plus machine learning. So hope I can help everybody. Okay, my name is Evan, and Ravi is my manager. We are from Intel Lab, Security and Privacy Research. Okay, short outline. We start from background of the ransomware, and then we talk about the issues of the classifier, and followed by the model fidelity and adversarial research, and at the end with a small conclusion. So we all know ransomware is a kind of a malware which hijack users' resources or machine, and then demand for payment. And based on the encryption, we know the ransomware can be divided into two categories: the locker and crypto. Locker doesn't use encryption, so the damage probably is reversible. And for the crypto ransomware, it causes real problem. And because the encryption, right, so the damage is very difficult to revert. And so this is the focus of our project. So typical steps of the ransomware start from the upper left corner, the distribution. And after infect the user machine, you will communicate to the C2 server, get a key or other binary, and then you will scan your C drive or even your shared drive. And then you will do encryption. And at the end, you can see the ransomware the page for request for payment. So because we focus on the crypto ransomware, so encryption step is going to be our focus. We use file input-output events try to detect the ransomware. So the purpose of our detector, we are going to be the last defense line of the endpoint protection or antivirus program. So if the antivirus meets the new ransomware, doesn't have a signature or fingerprint, etc., then our detector will continuously monitor the file I/O and calculate entropy. And when ransomware start to run, we will stop it quickly. So we can sacrifice a few files, and then we can detect it and then kill it, or shut down the machine and trigger some rollback actions. So we start from building the ransomware, and we download the 22K of ransomware from VirusTotal, and based on Microsoft and Kaspersky's label. And each sample will run for 5 minutes in a sandbox system. So it's a bare metal. There's no virtual machine here. And we also equip with anti-evasion mechanism. So we simulate the user activity like mouse movement or the keyboard input. Hopefully you can trigger more ransomware. And we also put decoy files or canary files everywhere. So this is the target of the crypto ransomware. If the ransomware touch our decoy file, we know this is a crypto one. And at the end, we collect 4.4K of the ransomware active sample. And the family distribution looks like pie chart here. So it contains a variety of the families. And the data we collect is behavior data. So basically the file input output events by the C# program. It's a PLC program. So for the real production, probably this program should be in the Windows kernel. Okay, so we implement the API file system watcher. So whenever there's an I/O event, our callback function will be invoked, so we can log the events. And we also calculate the entropy of the target files. So by the Shannon entropy. So when file got encrypted, the entropy will be high, close to 0.01, 0.1, sorry, to number 1. And if the regular file, the entropy will be 0.5. And this is the same sample data here. So basically, it's a CSV file, and each row is one time step or the observations. You can see there's a timestamp, event type, and file name, entropy, etc. So we choose very simple feature engineering method. So we just use the I/O events and entropy. So the machine learning, we start from 3.7K ransomware execution logs, and then similar amount of the benign data, and we do an 80-20 split for testing, for training and testing. The feature engineering we done is by the event type and the entropy. So basically, we categorize those raw data into a distinct numbers. So it will be a sequence of the number or time series data. And the algorithm we use is LSTM, the long short-term memory. It's a good, popular, recurrent neural networks, and good to catch the long-term dependency of the time series data. And also some simple SVM, the support vector machine, with the backup n-gram, n-go 1 or 2. The 2 means the 2 observation become 1 features. So can catch the adjacent features, the relation. Okay, so we use the typical ML pipeline, like data processing and then training and then do a validation. And the training library, we use a popular one like Keras and the scikit-learn or the Spark ML-lib. And the result here, you can see the accuracy for both algorithms is around 98, and FPI is 1 to almost 3%. So it looks like we have a good machine learning model. So we create a PLC program and try our model in the real world. So this program basically will sample the I/O event string continuously by a certain window and do a real-time inference. And we hope this program is a small footprint, making it a small footprint and run efficient and fast, so it can be part of the enterprise program. But after deployment, we quickly found a few issues here. The first one is a false alarm from some application. So when some program runs, the behavior really looks like a ransomware. And the second one is the size of a sliding window affect the detection rate. So sliding window is small and the detection rate goes down. And the third one is the ransomware cannot be detected early. So the following slide, we are going to focus on these 3 issues. So early detection issue. Detector need to stop ransomware early, or basically there's no value here. And the next question is when will ransomware start to do encryption? So it's a good thing that we have decoy file in the sandbox, right? So we can identify the rough starting time of the ransomware. So it's pretty simple here. There's a simplified execution log, and each box is an observation or time step. The red box means the event or the observation from our decoy file. So we know roughly the region of the starting time. So we go back to our data set and try to find what's the starting time of our data. So you can see the results here. The y-axis is percentage, and the x-axis is the time. So you can see when time goes by, right, more and more ransomware showing the malicious activity. But we also know from here, not all the ransomware start malicious activity at the beginning, right? So this makes dataset preparation a little bit tricky. So next question we try to answer is what's the performance of our model regarding the early detection and sliding window. So we prepare 700 unseen of sample ransomware logs. So it's not from the data set, either training or testing. And we extract the early stage data for each log. So one log become multiple samples. So the first one is early stage sample by the different time period. And the second one is a sliding window. So you can see the example here. This is a full size of a log for one sample. And then we slice the first part, the different periods of the time same data. So like 0 to 1 second or to 5 to 10 seconds, etc. And then we also exclude those samples doesn't have any decoy events. So we guarantee the sample we generate is malicious. And then the second set of sample is the sliding window sample. We further slice those early stage samples. So we have two sets of samples here. And then we use our model to try to detect them. So here's the output. So the green line is the percentage of the ransomware has a malicious activity, and the blue bar is the detection rate. So if you look at the rightmost column here, the detection rate is around 95%, and the green line and blue bar is very close. So it matches our result from our testing data set, right? High accuracy. But if you look at early stage one, you see there's a gap between green line and the blue bar. So we know some portion of the ransomware we cannot detect by our model. And if we put the result from the second set of the sample, the sliding window sample, you can see here different color means it's different size of a sliding window. So if the sliding window is smaller, detection rate goes down more. Okay, so this result is from SVM model. And ALSTM has a similar situation, but it looks like the gap is smaller and it's less sensitive to the size of a sliding window. So how we solve these issues? So it's very straightforward. We do a data augmentation. We modify our data set similar to the test we did prior. So we synthesize the early stage sample and the sliding window samples, and exclude those samples doesn't have malicious decoy events. So after we train, the accuracy in FPR is similar. But if we test by our sample here, you can see the gap has been closed, and also doesn't see much the effect of a sliding window. So we believe the data augmentation fix the two issues here. So next issue is false positive. When we observe many false positive samples, we found those behavior actually looks like ransomware to human too. So it will delete, rename many files in a short period of time, and also change file with high entropy. One example is like Google Chrome doing the updates. Somehow the behavior looks like ransomware in our observation. So the solution we have, we add the other dimension to the feature, the path. The path can label is from system folder or non-system folder. The system folder or whitelist here is like C drive Windows or C drive program files. Okay, so additional the dimension make it have more resolution to distinguish if it's malicious or non-malicious. So after we train, we do see the FPR. You can see the column on the right, the second column on the right. The green numbers really goes down compared to the one without had the pass flag. So, and we also test 22K of sample clean execution logs. The FPR goes down too. Okay, so next topic is model fidelity. We know we need to, for security, right? The model reliability is very important. So we need to make sure your model based on the correct information to make a decision. So the method we choose is called the integrate gradient. This is a method from Google's paper. And basically it calculates the attribution. So it can tell you which feature, time step, and contribute the most to the decision making. So here's a mathematical description here. So basically, it not just look at the gradient, you will accumulate the gradient along different value of the features. So we can look at output from the paper. The first row is a camera, second row is a firebolt. If you look at the middle column, the output from the integral gradient, each pixel, lighted pixel, the intensity means the contribution. So you can see the top one in the middle column, it looks like a camera already. So we know this model based on the correct pixel to make a decision. And same to the firebolt. They use the water and bolt to make a decision. So if you just look at the gradient, will be the column on the right. It's kind of blurry, it's kind of difficult to tell. And for the language processing, the sentence classification, similar results. The the highlighted words, like the first row, how many contribute the most to the prediction, the numeric. So I think this is a good method. So we apply this method to our ransomware sample. This is output from 250 size of the sliding window sample. So you can see for the clean region, the benign features here, there's nothing output. Okay, so look at the region at the bottom, you can see the blue bar. Blue bar is the output of the attribution. You can see a really cluster pattern here. And the orange bar is a label for the decoy file. So we can see the orange, the pattern of the orange bar and the blue bar basically overlap very well. So it really tells us the model used a correct time event or time step to make a decision. So the last topic is the adversarial research. We synthesize the ransomware, the rating by the C#. So basically, it will do the core business of the rename, the ransomware behavior, like rename, encryption, or deletion. And the evasive trick we apply has a twofold. One is it will change the pattern of the malicious behavior, like slow down the encryption or insert multiple benign events when doing the encryption. Or even change the encryption itself. We insert dummy data to the output, so make the output file have lower entropy, or even we partially do the encryption, not encrypt the whole thing. So we found it's not difficult to evade our ML detector, even it has a good accuracy. So how to solve it? Actually, it's pretty straightforward here. We try many different combinations of conditions for these two tricks, evasive tricks. And you know, this is a gray box attack, right? We don't know the model weights, don't know the model architecture, but we do need to know the model based on the I/O events and the encryption. And then we try several for many times, and then we collect all the false team samples and then do a retrain. And at the end, we found our rating is difficult to find the evasive sample. So we believe this method can improve the robustness of the model. And we also use the integral gradient to try to explain why the evasive sample can evade our model. So this is the typical sample of the ransomware. You see there's some output from the integral gradient method. So we do, the method we try is we insert a benign event in between the malicious event. It's kind of simulate the execution log. And we found the label have been changed and score become very low. So you can see the output from the integral gradient. The orange bar still label the decoy events. But you can see whenever there's an orange bar, it still has positive attribution to the decision. So the model still can recognize there's a malicious event. But the magnitude of the blue bar become very small compared to the original one. I think it's less than 10 times, so it becomes very small. So the benign events really dilute the effect of the malicious event. So I think that's why it got evaded. Okay, that's our conclusion for our experiment here. So in addition to the regular machine learning pipeline, we suggest to have data augmentation, especially when you have a small data set or the data set is very difficult to obtain. And like for our example, we do early stage samples and sliding window samples. And after you have a model, you need to check the fidelity and make sure your model based on the correct information to make a decision. And at the end, we suggest to have a simulated adversarial, right? You can probe or attack your model, and then you can collect the adversarial samples and for retraining. And then at the end, you can have a better robustness for your sample. Okay, introduce our team. We are a small team, other than Lee and India here. And this project is part of the MLSploit. MLSploit is a joint project between Georgia Tech and Intel. and it's a platform for ML model comparison and data sharing. For many is for the adversarial research. So if you're interested, welcome to visit our GitHub site. Okay, thank you.
Thank you, Evan. We have some time for some questions here.
Thanks. Very interesting talk. So you mentioned that like artificially sort of designed ransomware could evade your ML, but could you? Well, is it even possible to kind of add a filter that would dynamically look at the logs while it's just detecting whether there is some suspicious activity, so you could start contributing to like a set that would eventually be used in the machine learning model, and then the model will decide if it's false or like positive or negative, and then move on. So you don't have to like
I think it's possible.
It will be harder to evade it then.
It's possible if you pre-filter those data, right, and exclude those nonsense events. It's likely, yes, but we did not try that part. Yeah. Yeah. Thank you.
Thanks for the talk. Just a quick question on, you mentioned that using Shannon's entropy on, well, the question is, are you using it on the write or on the result of the malware interacting with the file? So you calculate it for every write or when the file gets closed?
Yes, we calculate the entropy for the modification events and for 1 megabyte of the initial of the files. And we try different type of the calculation. We found first 1 megabyte probably is good enough. The target file, yeah.
Okay, thanks.
Yeah.
Thank you so much for that presentation. First of all, I'm not an expert on ransomware, so I'm not really familiar.
Sorry, I cannot hear you.
Yes, can you hear me now?
Yeah.
Yes. So I'm not sure how ransomware actually executes, but my question is, you mentioned 2 types of ransomware. First of all, did your dataset include both types? And if so, did you see a difference in performance?
We did not try different type of ransomware. We will focus on crypto ransomware.
Okay.
The ransomware has an encryption. Yeah.
Do you expect a difference if you try the other type of ransomware?
We believe the data we use has many locker ransomware. Locker ransomware did not touch the files.
Okay.
So probably our program probably cannot catch their behavior.
Okay.
Yeah.
The other question that I also have quickly on the false positives, false
yes.
negatives. So you mentioned one example is the Google
Google Chrome.
So would Google Chrome go across different directories or different folders and change files, or is it like within?
Yeah, the Google Chrome, the folder they use, I believe is a program data or something. So it's belong to one of the system folder we define.
So that might be one way you can reduce that because
yes.
ransomware would go across different folders.
That's right. That's right. Yeah, so that's the purpose of the path flag.
Yes.
Yeah.
Great. Thanks so much.
Thank you so much for the talk. Just a quick question. Is there a reason that you found the windowing based on time more efficient than windowing based on event count? Because time is not necessarily homogeneous for different runs of the same ransomware.
Yeah, actually we tried both, and we found we use time step is easier, and the accuracy probably is similar. If you base on time, sometimes the 1 second has thousands of events. So yeah, it's a very huge. It made the detector very difficult to process. Yeah, there's more choice for us.
Evan, that was an interesting talk. I have a question. I think there's there's a lot of parts to this talk. One is about the hardening of the ransomware model. Also is the early time series part. I want to...
Sorry, you can't
the early time series part of that.
Mm-hmm.
So in a lot of the early time series literature, instead of creating discrete sections that grow in time, there's a tunable parameter that trades off between accuracy and earliness, right? So I wondered if you've explored some of those, or what your thoughts are about using that kind of framework with this other knob to tune. So there's now two knobs. There's an accuracy knob based on threshold, and then there's an earliness knob that trades between accuracy and earliness. What your thoughts are about those sort of approaches that are used elsewhere, not for ransomware.
Yeah, I did not think about this part yet. To us, I think we found, we try to make the classifier focus on not just encryption. So any event, the pattern from the early stage, you want to catch it. So that's why we put the 0 to 5, 0 to 1, right? Always from 0 instead of a kind of sliding window, right? So we'll hope the classifier can catch more than just the encryption. So actually in the SVM, we do found the top features actually become, from the encryption, become to like rename, or delete those n-gram equal 2, right? So it really shifts when we use the early stage data. So we did not try the parameter you talk, but we tried different way to try to have switch the focus of the classifier. So make it more smart to detect by the early stage patterns.
Thank you.
Yeah, thank you.
Let us thank our speaker one more time.
Thank you.